All right.
You do?
Oh yeah, we do.
Yeah.
Yep, conjecture booklet question 6. And part A just says, consider the function, sketch the graph below showing axes, intercepts, and the vertical asymptote. Okay, again, I'd be looking at this function and going, they give you the V window from -4 to +4 on the x-axis, -15 to +20 on the y-axis. All right. We also know there is a vertical asymptote at x is -1. All right. So if the function is x to the 3 on top of x plus 1, well, it's undefined when that denominator is 0. And we can see that asymptote occurring here. And if I zoom out a bit, I'm going to set my V window to the same as what they've got. They've got y goes up to 20. Okay, you can see the other part of the function there. All right, now we won't worry about sketching it in our books right now. We'll try and save time. The only thing I'll say is you're getting 3 marks there. So you're getting a mark for drawing the asymptote. And when we want you to solve the minimum, right, okay, when you're getting marks for solving the minimum, see how that minimum occurs at -1.5 and 6.75. So if we're going to sketch that, -1.5 and 6.75, you've basically got about 2 or 3 boxes that minimum has to appear in, okay? So here's the grid, and we'll have an allowance of like these 4 boxes. And we'll say the minimum has to appear in one of these 4 boxes. Let's say the minimum is occurring here, and we'll have that sort of allowance. As long as it's here somewhere, you're indicating that that's how you get the mark. So you do get marks for positioning things in the correct space, the vertical asymptote, and then the other feature would be this stationary inflection point. Okay, so making sure that it's in the correct location, that it's got the right shape, and so forth. Okay. The graph has 2 stationary points. One of these stationary points is at the origin. Find the x-coordinate of the other stationary point. So already we're on to A part 2. All right, the x-coordinate of this stationary point. All right, the slope is 0. G solve that minimum. The x-coordinate of the stationary point is -1.5. Okay. Your calculator might say 3 or 2, it might say -1.5. Alright, flip back. Now consider the function x to the power of n on n plus 1, where n is larger than or equal to 2. Find all passive possible values of n, g of x has 2 stationary points. One of them is always at the origin, and the other is point A. All right, so now here's where we're going to start to develop that conjecture. We've got n, and then we've got x coordinate of A. A is the other stationary point that's not at the origin. We have when n is 2, we've got -2 on 1. Now in part A, we've already done when n is 3. And this is an indication of how they want us to present it. Okay, they've given you a fraction in the first part, which means we should express this as a fraction in the second part. And already you might be able to start to see a pattern. Let's get the other cases. All right, so that means I need to sketch the function x to the 4. Okay, there's a minimum at 0. And another stationary point here. Okay, -1.3. That's the same as 4 on 3. And then x is 5. We're just changing that top number there. And 1.25, that's the same as 5 on 4. Okay, so we've got all of those values in there. So that's B part 1. All right, fill the table in, find the values. Okay, part 2. On the basis of your answers, make a conjecture about the x coordinate of the other stationary point at A. What's the x coordinate of A? So we're trying to make a link between n and this number we get here. When n is 2, the x coordinate is minus 2 on 1. When n is 3, minus 3 on 2. When n is 4, and so we're asking, what about when we use n? All right, so hopefully we can see. Can anyone tell me what it is?
Yeah.
Yep.
Minus n on intake 1.
Minus n on intake 1. Good. So this number is just the same number at the top, isn't it? And then the one below it is, well, just one less. Okay, so if we have 3, that's 3 take 1. 4, we have 4 take 1. So if we have n take 1, and the whole result is negative. Okay, that's our conjecture. Let's prove it. Now I've said we've really got two types of conjectures, 3 I suppose, but you don't tend to get points of inflection. So there's tangents and there's stationary points. And stationary point ones are all the same. You're always doing the same thing, okay? What are we doing? Stationary points occur when the first derivative is 0. So we have the function, the family of functions is x to the n on top of x plus 1. All right, that's the family of functions. Stationary points occur when the first derivative is 0. So we're going to find the first derivative and make it equal to 0 and solve for x. So if I'm going to differentiate this, I need to use the quotient rule. Smash it all together. U dash b, take away uv dash on top of b squared. All right, stationary points occur, so we've found the derivative. Stationary points occur when the first derivative equals 0. You get 2 marks just for doing that. 2 out of 4 marks, okay? So now we're trying to get through and we're trying to get this x value, right? So because it's a rational function, it's going to equal 0 when the numerator equals 0. We're only interested in this part of it. Okay, now we're trying to solve for x. We want to get x by itself. All right, so we're going to try and factorize something so we can apply some null factor laws or so and so forth. So, if I'm looking at these 2 terms, remember we pointed this out last time, okay? X to the n is a factor of this term, and I'll explain why. If I have x to the n take 1, that's the same as x to the n on top of x to the 1. All right? So I won't pull it out straight away, I'll just express it as I've done up there. X to the n on top of x. And then here we have times x plus 1. Yep. And then take away x to the n. That's a separate term, I don't need a bracket there. So now, if I'm looking at this term and this term, x to the n is common. Let's pull that out the front. And what are we left with? We're left with here n times 1 on x times x plus 1, take 1 equals 0. Okay, I don't want to rush this part because this is where the tricky algebra occurs. I've said x to the n is a common factor, so we've pulled that out the front. Here's what we're left with. We apply the null factor law. Either x to the n is 0 or this component is 0. And I'll deal with this component up here on my left board. So we have n times 1 on x times x plus 1, take 1 is 0. Now here, this gives you x is 0. And we know there's a stationary point at x is 0. That's for all of the functions. If you look at your graph, there's the stationary point of inflection occurring there. So we can disregard that solution. We're interested in this one. All right, we can plus 1 to both sides. We're solving through to x, right? So what have we got? We've got x plus 1 on x equals 1. All right, multiply both sides by x. All right, here we'll have nx plus n equals x. I'm going to move this nx term over. All right, so what have we done? Multiplied by x, move the nx term over. Here we can factorise x. All right. And then divide both sides by 1 take n. All right, now you might think it looks a little bit different to what our conjecture was. So we made the conjecture minus n on n take 1. But I want to tell you why these two are the same. All right, when I have a negative out the front of the fraction, it can apply either to the top or the bottom. So if I were to write it like this, okay, I'm applying the negative to the bottom. We're left with minus n plus 1 at the bottom, which is 1 take n, which is what we have. Okay, so that's a reasonably, follow the process, right? Differentiate it, make it equal to 0, and then all you're focusing on is the top part, and you just got to try and break that down, wrestle with that. How do I get x by itself to show that my conjecture is true? All right, very good, guys. So 3E, do as much of it as you can, and we'll catch up tomorrow. We'll go through 3F